Welcome, ladies and gentlemen. So we have to know how to calculate our simple derivatives, right? Our simple derivatives from last year. So if I'm differentiating an expression with respect to x, I can just apply, right, my derivative rules in order term by term. It looks to me like we'll go power rule. I know if y is given by 4x cubed minus cosine of x, then y prime is given by 4 times exponent times the base raised to 1 less. So we're looking like 12x squared. Cosine differentiates to opposite of sine, so negative sign becomes plus sine of x. And raise your hand if you had number 1 right. Did you have that already? You got the sign? Hey, way to go. That's pretty sweet. If y is given by negative 5 secant x minus 4 cubed, I can differentiate term by term and generate y prime. It looks like negative 5 is my constant multiplier hanging around for the party. Secant differentiates to secant x tangent x. And so the derivative of secant x is secant x tangent x. And the derivative of 4 cubed is not 12, right? 4 to the second. That's not a power function. There's no variable in there. That's just a constant. And the derivative of any constant is 0. So this is it. My final expression is negative 5 secant x tangent x. Go ahead and raise your hand if you had that. We've already had that. Hey, good news. 3. I is 3 tangent x, so let's see. Y prime must be given by 3 secant squared x minus 5 times, and this is an exponent. That's my notation for inverse cosine. We know the derivative of inverse cosine is opposite of 1 over the square root of 1 minus the input squared times the derivative of the input. For us, that opposite is going to take negative times negative 5 is plus 5 over square root of 1 minus x squared. And then minus pi cubed, the derivative of any constant is 0. So that's, ooh, can we grab this maybe? Maybe. Awesome. So I'm dying to know, did anybody get the inverse cosine derivative? Did you get number 3? Hey, that's good news. And then last on this page, go Gadron. We've got, an exponential function. So this is not a power rule, right? This is not a power rule. My base in that power expression is a constant raised to the independent variable. That's an exponential because my variable is up in the exponent. The derivative of an exponential is given by the exponential itself, right, times the derivative of the exponent times the natural log of the base. So this should be 3 to the x times ln 3. The base in this exponential wasn't the regular e. Plus, the derivative of natural log of x is one of my favorites. That's just 1 over x, right? 1 over the function times the derivative of the function. And the derivative of 19 is 0. Raise your hand if you had number 4 correct. Number 4 correct? Great, halfway there. So now I'll go ahead and, are you guys ready? I'm going to start calling on you now, right? You guys ready? We've had our warm-up, those first 4. We're kind of like waiting, testing the waters, and now you're ready to go. So get ready because I'm calling on you. All right. If y is 4x cubed minus cotangent of x, then y prime is, Riley?
That would be 12x squared plus cosecant x cotangent.
Yes, oh my gosh, that's right. Good job. So cotangent does differentiate to the opposite of, right? Opposite of cosecant squared x, and so minus a negative is that plus a positive. And remember, what goes to negative cosecant cotangent? What would differentiate to that?
Cosecant.
The other one, cosecant. Good job. All right. So right here, if you had this then. Go ahead, number 5. Good. Let's keep the party going. Ooh, number 6. For the first time, we see a product of 2 functions. And so I know that the derivative of a product of 2 functions is the derivative of the first times the second as is plus the first function times the derivative of the second. The derivative of sine of x is cosine of x. And so when I go through and do my first application of the product rule, the derivative of the first times the second plus the first times the derivative of the second. And there's not a lot of ways to make that look prettier. We could factor out an x if we wanted to, if we were going to set this equal to 0 and solve or do something, right, an application. But it's fine to leave it like this for now as we're computing derivatives. So 2x sine x plus x squared cosine x. Raise your hand if you had that. Did you get the product rule right? Hey, that's good news. All right, so let's do the derivative of, inverse tangent. So I'm going to call on you for this one. I know you guys know inverse tangent. That's one of my favorite derivatives. So what's that going to be, Vivian?
3 plus 2.
Good. And then minus 5 times log of x. What's that going to differentiate to? Remember, we got our log log is a little bit different than natural log. So who had that one? Danny?
5 over x ln of 10.
Nice work. You can generate this either using your change of base and rewrite a log of any base b as a natural log, right? ln of input over ln of base using our change of base formula back from pre-calc. Or we could use our log derivative of logarithmic function rules. It's 1 over the function, right, times the derivative of the function divided by the natural log of the base. Remember, logarithms and exponentials are inverses of one another. And so you think about doing kind of the opposite operations when you differentiate as you would perform when differentiating exponential. The derivative of an exponential is the exponential itself times the derivative of the exponent times the natural log of the base. When you differentiate a logarithmic expression, it's 1 over the function times the derivative of the function, and then divided by the natural log of the base. So you're doing the opposite operation there. That's pretty sweet. And I don't mean to yell, it's just I'm so enthusiastic. Tyler?
So 5 natural log of x over natural log of times the same thing.
5 natural log of x over natural log of 10 is the same as the original.
Oh.
Then when we that would be rewrite. Okay. Then when we differentiate, that 5 over natural log of 10 is just a constant. So here it still is, just a constant. And what's the derivative of ln x? 1 over x. You see what I'm saying? So that would be to rewrite a log of any base b, and the originally you write it as ln of input over ln of base. Good job. And we're one to go, and I'm raring to go. We had a product earlier. Let's do the derivative of a quotient of two functions. The derivative of a quotient of two functions is the derivative of the numerator, e to the x differentiates to itself, e to the x, times the denominator, minus the numerator times the derivative of the denominator. The derivative of the denominator cosine of x is opposite sine of x, all over the denominator squared. So there's multiple ways to rewrite this, but you don't have to. I might pull out an e to the x just because, have it, and get cosine of x minus sine of x, close numerator, all over cosine squared of x. Can I cancel out a cosine x? No, can't cancel out a cosine of x. It's not present in all the factors on top. If we're a factor out here as a multiplier, right? If it were a factor out here with the e to the x, then I could cancel out one cosine of x. But remember, every single term has to include a factor that's common with the denominator's factors in order to cancel out anything in a fraction. Nice job, you guys. Son of a gun. What a great Bellwork. I'm excited to get going today. What questions do you guys have about our derivative calculations? Sydney?
So I'm just wondering, like, is it ever going to be right or wrong if we pull something out or don't pull something out? Is there one way you prefer or not?
It depends.
Okay.
Typically, if you're going to do something with it, like where on the curve is the tangent line parallel to such and such, then we want to factor this out to set it equal to so we can solve or something like that. Then it's going to be easier to work with in fully factored form. Where is the horizontal tangent, right? Fully factored form would be easier to do that so that I could set the numerator equal to 0 and solve and see when that occurs or not. But no, I mean, I don't like this minus a negative. I mean, in the very least, where did that go? Shouldn't that be a plus?
Yeah.
Right here? When are you guys going to tell me that? Striving for PDF, right? Striving for PDF, come on, baby. So we gotta have this right. Oh my gosh, once we create the digital posterity and post on our site. All right, anybody other corrections that we gotta fix for Mr. Fritz? We're okay? You're holding back on? Awesome. Let's go ahead and get you credit for your book work. Keep your symbolic rule sheet. You got to stamp for that. Keep that. Don't turn it in. But your book work, go ahead and staple multiple pages together, and I'll stop the recording now while we take our homework check. So make sure you're working and preparing for your derivatives rules quiz, because I know you guys can do great. To that end, let's go ahead and add our words. And so we're going to add our words for our derivatives. The words take into account the chain rule that you're going to work to develop now using our highlighter activity. in the next part. So we're going to go ahead and work to develop our rule sheet. I wholeheartedly believe that by reading, by writing, by speaking, you're going to remember these words better, commit them to memory, and you'll remember them for longer. So the derivative of a power function is the exponent times the base raised to 1 less times the derivative of the base. Notice how this has the chain rule built into it. That times the derivative of the base takes into account the chain rule times the derivative of the inner function. So the derivative of a power function is the exponent times the base raised to 1 less times the derivative of the base. All of these are written again on the highlighter activity too. If you don't finish up a portion of it, you'll have access to them in just a minute on the highlighter activity. But I want you guys to write them. I think that there's value in that and seeing it yet again represented differently. The derivative of a product of two functions is the derivative of the first times the second plus the first times the derivative of the second. We saw our product rule in number 6 on our Bellwork this morning. So the derivative of a product of two functions is the derivative of the first times the second plus the first function times the derivative of the second. Not to be outdone, the derivative of a quotient of two functions is the derivative of the top function times the bottom minus the top function times the derivative of the bottom all over the bottom squared. You may use numerator for top and denominator for bottom, but you can't use first and second because we don't know what first and second is. So the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator all over the denominator squared would be another way to say that. The derivative of a trigonometric function is the derivative of the trig function with the angle, then times the derivative of the angle. The derivative of the trig function is the derivative of the trig function with the angle, then times the derivative of the angle. This is perhaps the easiest way to see the chain rule apply, right? The derivative of cosine of x squared. It's easy to see that chain rule apply. It's the derivative of the trig function. Cosine differentiates to opposite of sine with the angle, and then times the derivative of the angle. The derivative of my angle, x squared, is 2x. And this way you can see your words. The derivative of the trig function is the derivative of the trig function with the angle, then times the derivative of the angle. And of course we would rewrite that as negative 2x sine of x squared. It's easy to see that chain rule application in the trigonometric function words specifically. The derivative of an exponential function is the exponential itself times the derivative of the exponent times the natural log of the base. This works for all exponential functions, right? Whether it's base e or otherwise, like our derivative of 3 to the x we saw in Bellwork. The exponential function itself times the derivative of the exponent times the natural log of the base. I'm going to go ahead and add a function there, so we don't wonder, is that the exponent? Is that not the exponent? No, it's the exponential function itself. times the derivative of the exponent times the natural log of the base. Okay. The derivative of the inverse sine function is 1 over the square root of 1 minus the input squared, closed radical, then times the derivative of the input on top. So the derivative of inverse sine function is 1 over the square root of 1 minus the input squared times the derivative of the input. We saw that in Bellwork too. We saw inverse cosine. Which shares the radical term. The derivative of inverse cosine is exactly the same, but opposite of 1 over the square root of 1 minus the input squared times the derivative of the input. So the derivative of inverse cosine is the opposite of 1 over the square root of 1 minus the input squared times the derivative of the input. Neck and neck, one of my favorites, the derivative of inverse tangent. Yes, the derivative of inverse tangent is 1 over 1 plus the input squared times the derivative of the input. Two to go, guys, 2 to go. The derivative of the natural log of a function is 1 over the function times the derivative of the function. There's my other neck and neck race right there. Love the derivative of natural log. 1 over the function times the derivative of the function. And last but not least, the derivative of any constant is 0, right? There's plus 1 for sure on your quiz, right? The derivative of a constant is 0. Yes. Oh, you guys are done writing that one? That didn't take very long. So, what's up today? Well, we've got our simple derivative refresher. For our simple derivative refresher, we're going to do that first and apply our derivative rules to a nice, easy worksheet. You're going to check that with the posted answer key on our Moodle website, so you may use your smartphone or electronic device. At number 16, that's the end of page 2. After you check the first half, you get 1 stamp. After you check the second half of problems, up till number 32 is where I'll place that second stamp. And again, that's based on you checking with the posted answer key. After you've gotten your simple derivative stamp on 32, then it's time for you and your partner to work on the highlighting activity. So the highlighter activity is called developing the chain rule with highlighters. When you're done with the highlighting, you get 1 stamp, and then you have 9 short derivative problems where you select and use the appropriate rule. When you're done with the last one, number 9, you raise your hand and you get your final stamp. Your OTL tonight includes the chain rule application, and that OTL is written here, and I haven't put on the board, so I'm going to do so now. So once again, first, do simple derivative refresher, stamps at 16 and 32. After you've checked it, please come up to the front table and I'll issue stamps. Then you're going to work with your partner on the highlighter activity. At the end of highlighting, you get a stamp, and then a number 9 for a total of 4 in-class stamps. And your OTL number 1 includes chain rule applications, and I'll put that on the board. I'll go ahead and stop the recording.